Okay, so my name is Liz Carter. I actually used to spend my time in Riley Robb Hall. I did my PhD in biological and environmental engineering and then moved all the way up here to Syracuse. So I'm currently an assistant professor in the civil and environmental engineering department up here. I teach water resources engineering and how to use different data science and AI techniques to process global Earth observations. So those are the two places where I spend my time in teaching world. And today I'm going to talk about a project that was funded by WRI last year that seeks to use some basic principles from photogrammetry, so the science of making measurements from photographs, Edge AI, which is where we take a machine learning model that's been trained on a big computer and we get it to run on a tiny little microcontroller so that we can be processing data out at the edge where we're making our observations, and low power sensor networking to automatically map flooding in cities, which is a big problem that I'm going to talk a little bit about that we do not have a lot of data on at this time. So just some quick background. I'm going to talk about the three main types of flooding and break it down to these categories because we have regulatory frameworks for managing flood risk, and based on how that flood is propagated, we have different methods for quantifying what that flood risk is. Then I'm going to talk specifically about urban pluvial flooding, which is one of these subsets of flooding that has pretty widespread impacts. It's associated with essentially failure of the urban drainage infrastructure. And it's a type of flooding that we don't currently have a really strong framework to manage. So we don't have really good systems in place to provide relief or to kind of triage repairs and come up with mitigative policies to fix it. And so that kind of motivates why we developed a sensor network that could specifically automatically generate high watermark maps when flooding happens in an urban area. I'm going to talk a little bit about what our flood sensors look like and kind of how they work. And then I'm also going to talk about some of our plans for how we're hoping to use the data to validate hydraulic models of flood risk and to try to get better estimates of where flooding has occurred from satellite imagery. So that's kind of where we're going to go today. Very comfortable being interrupted if anybody has any questions. Right, so first, the types of flooding. And this is hopefully going to be a recap. So probably the main type of flooding that we talk about in the United States is a fluvial flood. So fluvial floods happen when water flowing through a river or a stream exceeds the channel banks and spills out into the surrounding floodplain. So when riverine flooding happens, adjacent to a known flowing body of water, and you can kind of just see here that when we have excess rain or snowfall, overflowing water can spill out and damage properties that are right by the river's edge. Coastal flooding is another type of flooding that happens adjacent to kind of a known water body. Coastal flooding occurs on the edge of oceans and also really large lakes. So the Great Lakes experience coastal flooding. And coastal floods are caused by a special type of wave called a storm surge. A storm surge is a very large wave that forms in the wake of a low pressure system or a storm that can cause kind of widespread intrusion of the water body onto the surrounding coastline. Okay, and then the last kind of flooding is pluvial flooding. So pluvial floods occur anytime local rainfall intensity exceeds the ability of the ground or engineered infrastructure to drain it away. So pluvial floods are associated with things like ponding, away from a water body. And, increasingly pluvial floods are associated with failures or under-parameterization of our stormwater management system. And so pluvial floods, because they can happen anywhere, they don't necessarily happen next to a known body of water, are a little bit more challenging to measure than other types of floods. And this matters in terms of how we provide relief for flooding. So in terms of the total number of lives impacted and total cost of damages, flooding is by far the most damaging type of natural disaster. And in the United States, in the past, 100 some odd years, we've developed a framework to provide relief to citizens who have suffered loss of life or property as a result of flooding damages. If we didn't have these mechanisms in place at the federal level, history has kind of shown us that the economic fallout can be devastating for local communities. So if you kind of go back, you can trace the recent history of US flood control infrastructure to a flood the Great Flood of 1913. So, pretty much this was a storm that happened in the early spring. There was a whole bunch of moist air that came up from the Gulf of Mexico, and it converged with the westerlies. And it propagated a storm that was a lot like a nor'easter, except for it spanned 11 states and it was generating tornadoes in its wake. So this was a really unique, really large storm event. And the epicenter of the storm, at least in terms of damages, was Cincinnati, Ohio. So in Cincinnati, there were levees around a river, and behind those levees sat the business district. So when this particular storm occurred, the entire business district was essentially wiped out overnight. So lots of lives were lost. The damages were pretty substantial financially in 1913 dollars, so $200 million of damages, not adjusted for inflation. And in the aftermath of this storm, the citizens of Cincinnati essentially got together and they put together a massive fundraiser to provide relief for the victims. And what they did with that relief funding is they hired an engineering firm to come up with standards to redesign the levees to protect the city if a similar magnitude storm event should occur again. And it was kind of in the aftermath of this particular event, with that money raised for relief for victims of flooding, that what we've come to know as the modern method for delineating floodplains came into play in the United States. So in 1917, also in response to the Great Flood of 1913, the Flood Control Act was passed by Congress. This is sometimes called the levees only policy. The federal government is going to kick in 50% of funds to build levees and dams for flood control along major rivers in the United States. But at that time, there were no standards for design or maintenance of this flood control infrastructure. So flash forward 10 years, extensive levee systems have been developed using funding from the 1917 Flood Control Act. And we have a flood on the Mississippi River that takes 500 lives and causes, again, hundreds of millions of dollars in damages and displaces 1 million individuals. So what came out of this is that building levees isn't enough. We need to build levees that are strong enough to protect us in the event of a flood. So the 1936 Flood Control Act follows up on the Mississippi River, or on the 1917 Flood Control Act. And we start seeing us adopting the floodplain management paradigm that we currently use to provide flooding relief in the US. So we're adopting those design standards that were piloted in Cincinnati in the aftermath of the Great Flood of 1913. So what is a floodplain? See if this one is automatically going to play. So the way we have come to think about flooding is kind of an artifact of what we were able to measure with regards to hydraulic variability in channels at the turn of the 20th century. So this these videos kind of show examples of what riverine flood events look like. Essentially, we are able to measure the water level in a river channel rising up. And then we're able to use nearby elevation data to kind of interpolate what ground area would be inundated if a similar event occurs again in the future based on those measured water depths. So this is just kind of what this looks like schematically. We're able to make measurements of the depth of water in stream channels over time. We use a simple probability density function to estimate what we call the 100-year flood event is, the annual maximum stream stage that we would expect to see with a 99% non-exceedance probability. So we have a statistical entity that we're dealing with here with a known depth associated with it. And then the regulatory floodplain is any of the land area that, based on elevation, would be underwater in the event of that 100-year flood event. So I won't get into all of this, but we are, as a nation, continuing to build flood control infrastructure and continuing to see flood events of sufficient magnitude to, push our funding mechanisms to the brink of bankruptcy. So we are trying to figure out as a nation how to adjust to flooding. Should we move humans out of the floodplains, or should we continue to try to constrict the floodplains in the US. And we are seeing that, the federal government cannot continue to take responsibility for all flooding damages without going broke. So in 1952, President Truman submits a proposed legislation to Congress that establishes a national system of flood disaster insurance. So since we can't afford to, pay for relief efforts directly to all citizens, the idea is that instead we will provide an insurance product that will be made available to people who are at highest risk of experiencing flooding, and that insurance product will be federally subsidized. And in 1954, we officially codify the current floodplain delineation methods that we use in place to figure out where that 100-year flood event is in space. So the people that live within that 100-year floodplain are the ones that qualify for this federally subsidized flood insurance. And that proposal is ratified by Congress in 1956. And so this is kind of an example of what the federally delineated floodplains look like in the United States. We have our Federal Emergency Management Agency flood zone designations. If you live within a special flood hazard area or a non-special flood hazard area, then you qualify for a federally subsidized flood insurance product. So homeowners policies and renters policies do not cover damages associated with flooding. If you get this federally subsidized insurance and you experience loss of property due to flooding, you get a relief payout for that. In 1973, the Flood Insurance Protection Act mandates the purchase of flood insurance for some homeowners in high-risk zones. Most insurance companies will require that you have flood insurance, even if you live in a state that's waived this flood insurance requirement in order to qualify for a mortgage. And, since its, modern form, the frequency and intensity of flood events impacting this country have continued to get worse. Kind of up until we hit, 2005 was perhaps the most expensive storm that the United States has ever had. Hurricanes Katrina and Rita caused more than $17 billion in flood damages. So what we have right now is a federal flood relief program that is based on the model of the 100-year regulatory floodplain and the National Flood Insurance Program. And we are struggling to keep up with the rising cost of flooding with that program alone. So that's it for my history lesson today. So you might have noticed that when we're talking about coastal flooding and pluvial flooding, we have a discrete spatial area where we can say, hey, the risk of flooding is higher here. And knowing that we have that higher risk region means that we can provide special assistance to people that are at higher risk of flooding. That helps us keep the cost of providing flood relief low and manageable. We can't provide these mitigative products, these flood insurance products to all citizens. It would be too expensive. So what we're doing is we are providing assistance to people who live in the regulatory floodplain. So now I'm going to talk about pluvial flooding. This is the type of flooding that occurs locally just because the rain fell faster than the ground and sewer systems could take it away. And pluvial flooding impacts more people, costs more money, and has more persistent health impacts associated with it than other types of flooding. So just to recap, with fluvial floods, we can provide relief with the National Flood Insurance Program, and we have regulatory floodplain management. We have alternative zoning next to rivers to prevent damages from fluvial floods. Same thing with coastal floods. But with pluvial floods, since we have no real method of knowing what the risk of pluvial flooding is from place to place, we don't really have any mechanism in place at the federal level to provide mitigation and funds for mitigation and relief. Pluvial floods are also associated with stormwater and flood control infrastructure failure. So these are, as our federal water resources infrastructure continues to age and continues to be stressed out with climate change, pluvial floods are becoming more and more of a problem. Okay. So just to kind of underscore how much aging infrastructure is playing into increased pluvial flood risk, these are the grades for dams, levees, wastewater, and stormwater infrastructure from the American Society of Civil Engineers 2017 Infrastructure Report Card. The Americans, or the ASCE, grades the state of American infrastructure, and the primary metric that they're using is going to be the state of the infrastructure and the federal funding gap. So if we have a certain dollar value worth of assets and we know how much it costs to maintain those assets, the funding gap is how is the difference in money available to maintain our infrastructure versus how much it would actually take to maintain our federal infrastructure. So in the United States, we have over 90,000 dams, 15,000 of which are considered high risk. We have 30,000 miles of levees protecting $1.3 trillion in infrastructure, and these are sorely underfunded. We have almost 15,000 wastewater treatment plants, many of which also process stormwater. So that means that both everything that you flush down your toilet and everything that goes down a storm sewer drain ends up in the same pipes and goes to the same treatment plant. And these have suffered from federal budget cuts since the 1970s. And we are currently facing about an $8 billion gap in maintaining our stormwater infrastructure just to get it in compliance with current federal regulations. So infrastructure is a really big part of why this type of flooding is occurring. These are a few images of what pluvial flooding looks like in Syracuse, New York. We very frequently have surface inundation events. They impact transportation, they bring down our power grid, and they have a pretty big impact on private housing. So the main source of floodwaters for our urban pluvial flood events are backups of the municipal combined sewer overflow system. So our surface flooding occurs most often when our stormwater infrastructure is backed up, and therefore the combined stormwater and sewage effluent are essentially getting pumped into people's basements or percolating up through storm drains and then standing stagnant on the ground. So these aren't just floodwaters. These are sources of contamination and potentially sources of – of, 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 So this right here is a map of Syracuse, New York. You can kind of see its little outline here. And the regulatory floodplain, so the fluvial floodplain is indicated in orange in this picture. So everything that is in orange, those properties have access to federally subsidized flood insurance. So if property owners or renters incur damages associated with flooding, there is a federal mechanism in place to provide relief. The blue spots recognize places where we would expect an increased risk of pluvial flooding, just given the local intensity of rainfall and local topography. These are kind of low spots on the ground that we think would fill up during, an average annual maximum rainfall event. And you can see that we have a lot more extensive pluvial flood risk, just modeled using rainfall and elevation, than we do land area associated with fluvial flood risk in the area. This map right here also has the calls to the city's 311 line about sewage overflows into basements for the year of 2023 as well. So wherever you see a black dot, somebody called to complain about raw sewage overflowing into a structure. So you can see that we are seeing pluvial flooding associated with backups of the storm sewer infrastructure in places where we wouldn't expect to see it just due to elevation and rainfall alone. So modeling flood risk modeling pluvial flood risk is a really challenging thing to do. And this is a really important public health issue. All right. So that brings us to the project of interest. If we are going to talk about managing pluvial flooding in the same way that we manage our riverine flooding and our coastal flooding, what we need is some kind of a spatial estimate of pluvial flood risk. This allows us to prioritize maintenance and management of storm sewer networks and other types of flood control infrastructure in a way that is a little bit less ad hoc than responding to citizen reporting. And it also can help us to start to quantify the magnitude of this problem and integrate management of pluvial flooding into some kind of a federal regulatory framework. So what my group is working on right now is developing a camera-based sensor that will both detect surface inundation associated with pluvial flooding and send out alerts to city officials about the pluvial flooding in real time. So this is an example of what a very raw prototype looks like that I just took a picture of on my desk right here. And essentially, we can get into all of the nitty gritty here, but this device is intended to be asleep almost all of the time. It periodically wakes up and it checks to see if it's moved at all, if something has jostled it out of position, and then it scans the ground to see if there is water or not in each pixel within the camera's field of view. The cameras on this device aren't collecting raw imagery. We're not taking pictures of people or cars or anything like that. What we're doing is we're using an algorithm that sits on this little tiny microcontroller right here. And that algorithm interprets what each individual pixel is measuring in terms of surface reflectance into either a spatial measurement of there is water here or there is not water here. We can combine information collected from the sensor network with 3D photogrammetric models of the neighborhood where the sensor has been collected. And we can extract information on each pixel's location in terms of latitude, longitude, and elevation from those 3D elevation models. And when we put all of that together in harmony, we have a device that uses very, very little electricity, periodically wakes up and makes spatially continuous measurements across its image footprint of whether or not there's water in all of these discrete locations. It then transmits water when it's been the maps of this water when it's been detected to a central server using two different options for networking protocols. Let me get into a little bit more detail about what this looks like. So the goal of our camera network is to just kind of look out on the scene at all times. When flooding is detected, it categorizes that image instantaneously into water or not water. When it reaches its maximum inundation extent, it's going to be sending a bitmap or a vector of zeros and ones indicating whether each pixel was flooded or not to a cloud location. And it's also going to be sending out a text alert to city officials, letting them know that inundation has been detected at certain specific locations. A little bit of the nuts and bolts of how this works. A convolutional neural network, which is a really common type of semantic segmentation algorithm, a computer vision model, has been trained on thousands and thousands of images of flooding captured from different angles. And that convolutional neural network has been bundled up into something called a TensorFlow Lite model. So this is a much simpler model that does a pretty good job of approximating what our more complicated AI models saw. And this simpler model can run on a very small microcontroller with limited processing power and using only a tiny amount of electricity. So the result is that as these cameras are taking images across multiple wavelengths of the electromagnetic spectrum of the scene, that image is instantaneously being classified into either water and not water on the fly. And then this right here, this flood map is what we're most interested in. And this represents a much smaller piece of data than the raw image originally represented. The fact that it's a smaller data object means that it's going to be a lot easier for us to get that data off of our flood sensor unit and onto the cloud. And then when each one of these cameras are installed, we go through something that we call the image georeferencing step. So if we know that we're going to be installing some flood control or some flood monitoring sensors in a neighborhood, the first thing that we do is we go out and we conduct a photogrammetric scan of the neighborhood. So a photogrammetric scan is where we take lots and lots and lots of photographs from different angles of the scene. Each photograph has associated with it the geographic coordinates of where the camera was when it was taken, and also information about the orientation of the camera within those geographic coordinates. We then use another type of artificial intelligence algorithm to find out where those images that have been many images taken of the same thing, we then overlap them based on common features that are observed in the images, and we can reconstruct very detailed 3D representations of space in that way. If we have that 3D model, that 3D photogrammetric model of a neighborhood, and we install a stationary camera with a footprint overlapping with that 3D model, we can use the common features between what our camera sees and what exists in the 3D model to get the latitude, longitude, and elevation associated with each pixel in our camera's field of view. So in this way, what we're doing is we're taking cameras and we're turning them into sensors that are making lots and lots and lots of measurements over the presence or absence of water over a spatial area. So we're automatically generating flood maps using cameras that are just existing out there in the world. So we generated these flood maps, and if we are actually in a disaster event, we have to be able to get the data off of our sensors fairly quickly, and we have to be prepared with a little bit of redundancy in case cellular networks have gone down. So our camera-based sensor nodes have all been equipped with the ability to send the data out to a server using either a cellular antenna or a LoRa antenna. So LoRa stands for Long Range Wide Area Network. We are able to generate a LoRa network by having a LoRa gateway. So we have a little device with an antenna that creates the signal and it can speak to our sensor nodes. And then that ties back into the internet. So, this is kind of a very portable wireless communication network that we can create in different locations with limited equipment and limited access to power. The pros are that it takes very little energy to send and transmit messages via LoRaWAN. It is fairly secure. And again, it is portable, so we can set these devices up fairly quickly. The cons are that we have to be working with very, very small data volumes. So we would never be using a LoRaWAN signal to send or transmit a whole image. A whole image takes up too much space. It wouldn't be able to get through that network. But we can get our compressed classified images, our flooding bitmaps, sent over LoRaWAN fairly handily. So the current vision, kind of moving forward, we've got our flood cameras out there, and what these are supposed to do is they are supposed to automatically generate high water mark maps of standing surface inundation in urban areas. A lot of the flooding risk associated with stormwater infrastructure in urban areas actually happens underground. So what that looks like is that the stormwater sewers are becoming saturated, and it is causing them to back up somewhat unpredictably in different parts of the system. We see a lot of problems with basement flooding in particular associated with backup of stormwater sewers. So we are currently synchronizing our flood mapping sensors with stormwater sewer stage sensors, so that these can work together and be able to detect water both above and below ground without using a lot of power to do so. So the way this works is we have LoRaWAN enabled sewer stage sensors, and they detect when the pipes underground are running full of water. When that is detected, it sends a signal to the cloud via LoRaWAN that, hey, we've got water in this area. The cloud then sends a signal down to our flood sensors, which wakes them up and toggles them into something called emergency mode, where they start watching for surface inundation around the region of the storm sewer network where we detected saturation in the pipes. And right now, our stormwater sewer, our sewer stage sensors, too many S's, are also set up to send automatic alerts via the National Weather Service in certain communities in the US. So this is an example of what these storm sewer stage sensors look like in Madison, Wisconsin. So these are pressure transducers that are installed in the on the side of the street grids that feed into the stormwater lines underneath the street. This is just sitting here waiting for water to overtop the sensor, in which case it'll make a measurement of the water's depth. This right here is a little LoRa transducer, and so this is sending the data measured by this sensor out into the cloud. And all three of these sensors have been installed in Madison, Wisconsin by the Upper Midwest Water Science Center, the USGS branch up there. So here's one of these stage sensors on a street grid, networked to a data dashboard in Madison, Wisconsin. And you can see this sensor was measuring that it had 0.4 feet of inundation above the road surface at a given time. The USGS technicians were able to come back after the fact and observe a high water mark line, confirming that the sensor was accurately detecting road inundation. The storm sewer networks that we're going to be syncing our flood mapping cameras up with in Madison are in the process of getting connected to the National Weather Service local alert system. So the goal here is that when our automatic flood detection network sees flooding, it will both toggle flood alerts on road signs to alert motorists that there might be road inundation up ahead. And we'll also be able to send out text messages to users within an area of interest, that there is a flood alert in place. So this is an upcoming project that we're pretty excited about, integrating with the Urban Flood Detection and Warning System IoT networks in the Upper Midwest. The other thing that's exciting about having an automatically generated flood map that's based on observations is we can start to validate the flood inundation maps that are being generated using other means. So, currently, if you want to evaluate flood risk, riverine, coastal, or fluvial flood risk, you're probably using a hydraulic model. You're probably using a kind of a physics-based model that is predicting where water is flowing along the landscape based on elevation gradient, the energy profile of the water itself. And the modeling frameworks that we're using to predict flood risk have been around for a very long time. And we, up until recently, have never really had data available to validate how well they're working at predicting the spatial distribution of flood risk. So these maps right here are from a 2018 paper that was comparing hydraulic riverine flood risk. Hydraulically modeled riverine flood risk to observations of actual inundation derived from the MODIS satellite. And this paper found that the hydraulic models were chronically underestimating the distribution of inundation, which is observed by the satellite. And you can see that in light blue, where the observed and predicted with the hydraulic model is in dark blue. So if we can generate some observation-based flood inundation extent maps, we can use those to validate and hopefully better calibrate our hydraulic models. So this is one way that generating some automatic high water mark maps can help us better model flood risk in other places. The other thing that I'm excited about trying to do with our automatically generated flood maps is to create labels to help us improve our algorithms for satellite-based flood mapping. So I have been working for several years with the Intelligent Systems Group at NASA Ames, and they've developed something called the Deep Earth Learning and Training and Analysis Toolkit. This is a Python library that allows you to train convolutional neural networks on multiple classes of satellite imagery. A really important part of how this particular package works is that it's something called a transfer learning protocol. The Intelligent Systems Group went through and they trained something called a variational autoencoder on thousands and thousands and thousands of images from each one of the compatible satellite platforms. And we can use these variational autoencoders as a pre-baked kind of not all the way done model that allows us to differentiate different Earth surface features. And it helps us to get a more accurate classification algorithm for our particular surface feature detection application. In this case, we want to be able to see water with less training data. So if you have training data, which looks like an already delineated map of where there was water and where there was flood, you can use that to train a neural net classifier. And then you can take input images where you don't have any information about flooding extents, pass them through that trained neural network classifier, and get a flood map on the outset. So the big bottleneck that we've had towards developing, computer vision algorithms that will process satellite imagery, and this isn't just a flood mapping problem, it has to do with a lot of different environmental applications, is that we in general don't have really good labels for our satellite imagery. So we don't really have methods in place to create spatially continuous estimates of the presence or absence of the feature that we're trying to detect at a scale that allows us to get really good classifiers for our satellite imagery. So we have something called a training data bottleneck. We're not able to create good enough maps of flood extent to create classifiers that can get that information out of satellite images. And so we need to, this is just kind of an example of what a bunch of different worldview images of known flooding look like with different types of distortion. This is from the current training data set for the operational AI that's used by the federal government to detect flooding in satellite imagery. And their current bottleneck is they didn't have good ground truth data about what surface inundation looks like in complex terrain, under vegetation canopy, and specifically in built environment and in urban areas. So because we didn't have good labels of what flooding looked like in cities, our current flood detection algorithms don't work very well in cities, which is where some of the impacts are highest. So our satellite imagery is giving us lots of good information that could, or lots of good data that could be translated into information about flood extents. But because we don't have labels or really good maps of actual flood extents to train these algorithms, we can't extract that information from satellite imagery. So I'm hoping to be able to use some of our automatically generated flood maps. Though they are small, they will hopefully be accurate and mighty so that we can start to detect inundation in urban contexts in satellite imagery. Right, so this is just a quick summary of the design objectives for our urban flood observing network and the approach that we're using to get around it. Yeah, and then I'm going to go straight here and leave this open for questions. And if anybody wants to hop onto our GitHub repository and see what some of the code looks like on our little flood mapping box, you also have a list of all of the supplies needed to build one yourself. You can scan that QR code and you can get linked to that. So just to summarize, we need data on flood risk for flood management. And because we don't have data on pluvial flood risk, that means that pluvial flood events are largely excluded from our current regulatory and relief frameworks. So our plan is to use photogrammetry, edge AI, and low power sensor networking to generate an Internet of Things network that can automate pluvial flood mapping. These flood maps can be used to validate hydraulic models and to train algorithms that can extract flood extents from satellite imagery. So hopefully having a small number of these automatically sensor network generated flood maps can help us get insight about urban flood dynamics that extends beyond those sensor footprints.
Thank you. Thank you very much, Liz, for your research and for sharing the results. It's really very interesting and makes you think of all these, new kind of technology applications that can be applied to management and, different career opportunities that are kind of now available to many of your grad students to support environmental work through some of these skills and knowledge. And I thought that was very fascinating. Great. Well, I'm going to provide a little more context within New York's Great Lakes and some background on the flooding and sewage pollution risk and how this project is helping us to understand those management needs and apply, innovative approaches. And this project was supported with funding from the New York State Department of Environmental Conservation's Great Lakes program under the Ocean and Great Lakes Ecosystem Conservation Act funding within New York State's Environmental Protection Fund through a partnership with the New York State Water Resources Institute and helps to achieve some of our shared goals for flood risk as well as sewage pollution risk in New York's Great Lakes Basin, which I'll be, like the footsteps in the snow here at A-Bay, Alexandria Bay. I have an agenda to guide our path forward, and I'll be doing a very brief review of the Great Lakes Action Agenda that was updated in 2023, which I hope you are all familiar with. And I'll be talking specifically about the Great Lakes Action Agenda, flood risks and sewage pollution context within that agenda. I will, build off of what Liz had talked about from the federal perspective, history and policy to share some actions in New York to address flood risk and sewage pollution, as well as recent policies that are relevant to some of these issues and goals. And again, quick review. Goals of the Great Lakes Action Agenda, updated in 2023, include reducing or eliminating releases of persistent toxic substances, which, can come from wastewater discharge, controlling sediment, nutrient, and pathogen loading, which, wastewater discharge can also be a source, conserving and restoring native fish and wildlife and their habitats, protecting habitats from impacts, preventing and controlling invasive species, enhancing community resiliency and ecosystem integrity, assisting communities with understanding their risk and management actions that can help reduce those risks, and revitalizing local communities through sustainable management and stewardship. And we have also expanded cross-cutting priorities that apply to these goals, which include promoting diversity, equity, and inclusiveness, as well as, work to benefit disadvantaged communities and environmental justice areas that have been identified as part of the Climate Act and, environmental justice work. Educating the next generation of Great Lakes stewards, integrating traditional ecological knowledge and indigenous perspectives to, acknowledging that we are all within the native tribal lands of the Haudenosaunee, and, building relationships to, reconcile some of the past, takings of lands and the need to integrate, indigenous land management practices into, our sustainable management, and recognize that seventh generation value to sustain our land and water resources. Strengthening local capacity engagement and partnerships by supporting municipalities, engaging with organizations and researchers and other professionals that can provide support to municipalities and to support some of these Great Lakes issues. Innovating and elevating Great Lakes restoration through really very innovative research practices such as the one that Liz is sharing here today, and others that might come up as this whole new realm of technology with artificial intelligence and sensors and machine learning can be applied to innovative approaches. Accelerating the collection of and access to science, holding these types of webinars to communicate results of these research projects, and ensuring communities can have access to information about their flood risk, about their pluvial flooding risk, about pollution risks, to help guide their decisions, and also preparing for and adapting to a changing climate. As you'll see with climate change in the Great Lakes, we anticipate to see all kinds of effects, including increases in precipitable water in the warmer atmosphere, and the change in frequency and intensity of storms, less winter snowfall and more rain, as we've seen this winter, more intense precipitation events, as they're seeing there in Syracuse, with more pluvial flooding, increases in evapotranspiration, the plant uptake of water, and the in-lake effects of higher evaporative losses, and nearshore effects of more evaporation as well. So having a good understanding of how these changes are going to impact communities is important. And within a New York context, we have many policies and acts that have been more recently introduced, and statewide initiatives that are integrated within the Great Lakes Action Agenda to promote their application in New York's Great Lakes. And more recently, the New York State Climate Impacts Assessment was at least technical reports were shared and are available on that climate.newyork.gov, which can be used to help evaluate trends in climate impacts over time. And we have the natural resiliency measures guidance that can be applied to flood risk management to conserve, restore, and construct nature-based approaches to reduce erosion and flood risk. And the guidance features 17 different natural features and details how they can reduce some of those flooding as well as erosion risks. And the flood risk management guidance that was also developed under the Community Risk and Resiliency Act provides guideline elevations for structures and provides other guidance to determine design flow elevations for infrastructure to account for enhanced future physical risk due to storm surges and flooding. And there's lots more information in the Climate Leadership and Community Protection Act. There's a whole scoping plan that's almost 800 pages long and really highlights the need to support disadvantaged communities to overcome, barriers and support and opportunities to support them, including working with them to help address the disproportionate impacts from climate change that are being seen, and that's available through the Climate Act, climatenewyork.gov website as well. So the flood risk management guidance, this builds a little bit on what Liz was saying, but this is some of the specific New York guidance, which calls for elevations within flood risk areas of +2 feet or 3 feet for critical infrastructure to the base flood elevation. It also calls for climate-informed siting, future flow predictions, critical facility protection, and design flow elevations for transportation infrastructure with a summary of existing floodplain regulation standards and flood risk data and tools. And we've seen, more and more recent legislation to protect New Yorkers from flooding with under Governor Hochul. This recent legislation establishes a flood risk right to know for home buyers, where that it eliminates a previous credit provision and allows the requirement of the disclosure of information concerning flood risk, flood history, and flood insurance on real property transactions, which can include pluvial flooding. And there is a need to better understand this flood risk to disclose those concerns. And there may be a way that the FloodViz camera can be used to help understand those flood risks and these vulnerable communities, and where disclosure is needed, as well as where mitigation action is needed. And we also had the state of the state include a comprehensive resiliency plan to protect New Yorkers from extreme weather, with a number of provisions that could be applied there in Syracuse and could, leverage information from the FloodViz sensor to be supported. We have, creating, protecting our homes by creating the Resilient and Ready program, creating the Blue Buffers voluntary buyout program, the directing the Codes Council to overhaul building code design to have some higher standards for, temperature and precipitation extremes, protecting communities by making investments in statewide disaster response. So, having that real-time data go to signs to let people know that there's a road hazard can be, really help to meet some of that goal for, responding to state disasters and preparedness and at addressing, evolving threats. And equipping localities with tools they need to fend off floods and keep the lights on. So this is a direction for the Division of Homeland Security and Emergency Services to provide, things like pumps and flood barrier technology, and then developing a comprehensive adaptation and resiliency plan to equitably adapt to climate change and assess impacts to disadvantaged communities, ecosystems, infrastructure, and vulnerable economic centers, as well as giving the public tools to understand and act on climate risk. Again, the FloodViz sensors, they can provide more accurate projected floodplain mapping tools and support some of that, understanding of increased storm intensity. There's many more. There's releasing the climate projections from the climate impacts assessment, updating coastal erosion hazard areas, protecting vulnerable New Yorkers under the extreme heat action plan, which is kind of a shift from the flooding, what we do when there's not enough water and when it's too hot, and protecting New York's infrastructure by repairing aging flood control projects and removing hazard dams, launching a supercharged green resiliency grant program to build green infrastructure, which I'll talk a little bit more about as well, and prioritizing investments in our waterways and streams, expanding climate smart communities, and updating scoring method for funding water infrastructure to prioritize asset management and resilience to climate change. So there's a lot of provisions in there that are moving forward to support some of this resiliency work. And I would encourage you to check that out. I did want to touch a little bit on some of the DEC information available on combined sewer overflows, especially within disadvantaged communities. Here we have, that area where this study was taking place in the south side of Syracuse, showing that we have these combined sewer overflow outfalls with, some context where a combined sewer system collects rainwater, runoff, domestic sewage, and industrial water. It transports the water collected to a wastewater treatment plant and discharges treated water to nearby waterways under a state pollutant discharge elimination system permit. However, during wet weather, such as extreme rainfall events, the volume of combined wastewater can sometimes exceed the capacity of the wastewater treatment plant. And when this occurs, untreated or partially treated combined water discharges from an outfall, can be directly discharged to a nearby stream, river, and other water bodies, which is called a combined sewer overflow. Now, sanitary sewer overflows are discharges of raw sewage from sanitary sewers and are prohibited. SSOs can release untreated sewage into basements, or they can come up out of manholes and onto city streets, as Liz had talked about, depending on where this is. And these concerns about sanitary sewer overflows can be reported, and municipalities are required to notify the public about these types of events via New York alerts. And you can subscribe to New York alerts by signing up at the link at alert.ny.gov. So you understand those risks. And you can also look at past reports of sewage discharge events through the Sewage Pollution Right to Know law, if you were to search that. And other questions about this can be directed to Division of Water by emailing dowinformation@dec.ny.gov. And one of the practices that the Great Lakes Action Agenda promotes to address the impacts of flooding and manage also stormwater is this green infrastructure for wet weather. And green infrastructure has multiple benefits for reducing flooding and erosion risks and can be implemented in wet areas to absorb runoff, reducing the amount of water entering the sewer and having to be treated by the wastewater treatment plant during wet weather. Onondaga County has a very robust Save the Rain program and comprehensive stormwater management that's intended to reduce the amount of pollution that's flowing, from their, streetscapes and, pollution that is getting into Onondaga Lake. So they use a lot of green infrastructure, including rain gardens and green bioretention and reducing impervious or paved surfaces, and also by preserving and restoring natural landscape features and stream buffers to improve stormwater management. So, and they do a lot to promote awareness about stormwater and encourage practices on private lands. So that's a really great program helping to address these risks. And, within our Great Lakes Action Agenda, we have a lot of information on different funding resources that are available to support this type of work. And I'll highlight that for climate change, mitigation, adaptation, and resilience, to consider applying to DEC's Climate Smart Communities program, DEC's Water Quality Improvement Projects program. The National Oceanic and Atmospheric Administration has a National Coastal Resiliency Fund. The Environmental Protection Agency has Great Lakes Restoration Initiative funding, and New York State's Environmental Facilities Corporation has a Green Innovation Grants program, along with Water Infrastructure Act funding for improving wastewater and sewer infrastructure as well. And with that, I'll say thank you, and let me know if you have any questions about some of this New York State context, or feel free to ask Liz questions about her project as well.
Thank you, Emily. Thanks so much for contextualizing that work and providing so much great background and resources on everything that landowners and communities can do to sort of tackle these challenges.